do we mean by that? What we mean is that E and dA have to be either parallel or perpendicular. If they are parallel, then E dotted with dA, remember dot product would become E dA cosine theta, theta would be 0, and so that cosine term goes away, just becomes 1. Or if they are perpendicular to each other, then E dotted with dA, we'd get a cosine of 90 degrees, and that term would be 0. So either way, it's going to simplify our math. Okay? And then we use Gauss's law to calculate E. Now, I want you to look at what I wrote there. I said we use Gauss's law to calculate E, but I didn't put a vector sign on top of it. Okay? What we are calculating here is the magnitude. Tells us the magnitude of the E field, but it doesn't tell us the direction of the E field. The direction of the E field has to come from the symmetry of the problem, back here in step 1. And when we do a couple examples, you see exactly what I mean by that. Okay? So this is sort of the goal of Gauss's law. Use symmetry to simplify this equation such that you can calculate an E field in magnitude. All right? And let's see how that works. Okay, so in this case, we had a flux of 7. Namely, there are 7 lines of electric field coming out of our closed surface. But Gauss's law says that it's proportional to the enclosed charge. So in this case, we just had 1 charge in there. So if I add another charge in there, how does this work? Let's try a different color. Let's see if we can do blue. Let's say I add another positive charge right in the center. Okay, they're supposed to be on top of each other. In that case, that will also make electric field lines that are pointing radially outward. And those electric field lines will also poke through the surface. Okay, so here they come. And now what's the total flux? Well, the flux from the green was 7. The flux from the blue is also 7, right? 1, 2, oh, we got this one. 1, 2, 3, 4, 5, 6, 7. And so the total now is, of course, 14. Now, again, this is just a number. There's no units ascribed to this right now. And in some sense, it doesn't really mean much physically because we are just talking about a graphical picture of this electric field. More charge in there means more electric field lines coming out, means more flux through the closed surface of our Gauss's law. Okay, what happens now if we change that positive charge, the blue one, to a negative charge? Let's take a look at that. So let's change this positive charge right there to a negative charge. So instead of another proton, maybe now it's an electron. And we still have our positive one sitting right there. How would this picture change? Well, if they're really right on top of each other, the only thing that's going to change is the arrowheads. Right? A negative charge has electric field lines coming towards it, not going out. So let's change all the arrowheads to the other direction. Okay, now all those field lines are going to be pointing in. Here they come into the surface. And now what do we say about the total flux? Well, flux is how many lines are going through the surface, but there's a direction to it. The greens are positive because they're going out of the surface, but the blues are now negative because they're coming into the surface. And so what's the total flux in this case? It's 0. 7 minus 7. Okay, but is that consistent with this? Flux is proportional to the enclosed charge. If there's 0 flux, that means there must be 0 enclosed charge, and that is in fact the case. We have a positive, but we have a negative. So the enclosed charge is in fact 0, and in some sense it doesn't really make sense to draw any of these electric field lines because there would be no charge there. If the proton and the electron were really right on top of each other, there would be 0 electric field around it. Okay, so this is sort of a brief introduction to Gauss's law, and next lecture we're going to look at understanding this mathematically. Cheers. Hello class, Professor Anderson here. Let's see if we can calculate the E field of a point charge, and let's do it using Gauss's law. So we know what a point charge looks like. Here's our point charge, let's call it positive Q. And that point charge has an E field that is pointing everywhere, radially outward. And you'll see why I'm going to draw it with dashed lines in just a second. Okay, so there's the E field around my point charge plus Q. How do we calculate this E field using Gauss's law? What is the approach? Well, the first thing we do is we write down Gauss's law. So we know exactly what Gauss's law is. Gauss's law is the following. Integral E dot dA equals Q enclosed over epsilon naught. Once you write down Gauss's law, you need to draw a surface. So let's draw a surface around this thing. And since we have spherical symmetry, let's draw a sphere. And now you see why I drew it with a dashed line, because the E fields are inside until they poke out through the surface. So this is what I'm trying to represent here. Fields are inside this ball, and then they poke out through the surface. The left side of this thing is the total flux, right? This is the flux coming out of our closed surface. As Gauss said, it's proportional to the enclosed charge. So one thing that we can do right away is let's put a radius on this sphere. So we're going to say that this radius is r. Okay? You can draw any size sphere you want. Call it r in radius. We also need to think about dA. What is dA in this case? dA is a surface area element of the sphere. So if I think about the dA, it's a little slice of surface area that looks like that. Okay? But an area has a particular direction to it, and that direction is always perpendicular to the plane of that surface. So if you have a little piece of the sphere, dA is going out, which is good, because we know that E is also pointing out. Right? Everywhere E field is pointing radially outward, we can say E has a radial component that's exactly parallel to dA, and that's going to simplify this quite a bit. The other thing that we can say is E anywhere around on the sphere has to have the exact same magnitude. Why? Because it's always R away from the point charge. And by symmetry, if you flip the whole problem over, you have to get the same result, right? You have to get an E field that has the exact same strength over here as it would over on the other side. Okay, so what does this equation now become? Well, it becomes quite simply this. Integral of E dot dA becomes E times dA times cosine of the angle between them. All of that is equal to Q enclosed over epsilon naught. But we just said that E is a constant in magnitude around the whole thing, and so E can come right out of the integral. E integral dA. We also said that phi is the angle between E and dA, and that is 0 degrees, right? E is this way, dA is the same way, they're parallel. All right, this is looking good. It's going to simplify quite a bit. What does this whole left side become? Well, cosine of theta, cosine of phi, if it's 0, that thing becomes 1, and so we're just left with that. Over on the right side, Q enclosed is just positive Q, right? It's just one charge that's in there, positive Q, and so this becomes Q over epsilon naught. And now look at this right here. Integral of dA, closed surface integral. What does that mean? That is the area of the sphere, the surface area of the sphere, right? Pretty cool, because that whole thing just becomes 4 pi r squared. That's the surface area of a sphere. Equals Q over epsilon naught. And now we are basically done. We just have to divide, and we get E is equal to 1 over 4 pi epsilon naught times Q over r squared. And that's the electric field of a point charge. Now, you look at this answer and you say, okay, that looks right, except I don't have any direction there. Where do we get our direction from? The direction comes back from the symmetry in the problem. When we first wrote this down, we said the symmetry of the problem means the electric field has to be pointing radial. It's either radially out if it's a positive charge, it's radially in if it's a negative charge. In this case, we had a positive charge, and so we can get to our final result. You say E is 1 over 4 pi epsilon naught, Q over r squared, r hat. Okay. Electric field of a point charge calculated using Gauss's law. All right, hopefully that's clear. Cheers. Professor Anderson here. Let's talk about a gravitational problem. So in this problem, we have 4 masses, each of the same mass m, that are arranged on the corners of a square. And the square has side r on each side. The question is, what is the force on this guy right here due to the other 3? So this is Newton's universal law of gravitation. Right? Newton's universal law of gravitation says any 2 masses in the universe are attracted together, and the relationship is given by this. F equals negative g m1 m2 over l squared. So the negative sign means that they're attracted together. It's along the line between the 2 masses. Mass 1, mass 2, r is the distance between them. So since all the masses are the same in this problem, that simplifies this quite a bit. But what we need to worry about is sort of the vector nature of these forces. So let's think about this particle in a little more detail. Okay, here's my object, right there, but it's sitting on the corner of this square. Let's just draw one of the particles and see if we can calculate the force due to that one. So let's look at this particle right here. What is the force on my yellow guy due to this pink guy? Well, it is clearly along the line. It is clearly going to be towards the other guy. And it's going to have some particular strength. Let's see if we can write that out. And we'll call this F1, the force due to one of the others. F1 is going to be equal to, and we don't have to worry about the negative sign because we're going to add that indicates the direction. So it just becomes G, M of this one, and then that one gets us an M squared, and we're dividing in a particular direction. And so let's call this the X direction, and we'll call this the Y direction. So what is the force? It is in the X direction, which is an I hat. Okay, but that's not the only mass that is pulling on this test mass. We have another one right here. Okay? And that blue one is now going to apply force in this direction. And let's call that F2. What is F2? Well, let's see if we can figure it out. F2 is going to be gm squared divided by how far away it is from the other object. And then, of course, we have to square that. But we don't really know what that distance is. We need to figure it out. Right? This is a triangle. This side of the triangle is r. This side of the triangle is r. If those are both equal, then this is a 1, 1 square root of 2 triangle. And so this becomes root 2 times r. So what do we have down here? We have root 2r quantity squared. And now we have to be careful about the direction here. It has an I hat component. It has a j hat component because it's going up at this angle. And so we need to worry about that. The way we do this is there's some component in the I hat, cosine theta, I hat. There's some component in the j hat, which is sine theta, j hat. And that theta just happens to be 45 degrees. And so we'll be able to plug those numbers in and simplify that bit. All right, so if there's one final force, which would be close due to this guy over there, and that's supposed to be green, but it's a little yellow. That causes the force going up, which is F3. So what is F3? F3 is, again, gm squared divided by how far away it is squared, which is just r squared. And that is all vertical, and so we put j hat on it. Okay. So now what do we do? We're looking for the overall force on this particle right here. F. But that's not too bad, right? It's just a vector sum of F1 plus F2 plus F3. And now we know all of those numbers. F1 is gm squared over r squared times I hat. F2 is this thing. Gm squared, let's square out the bottom just a little bit. Let's square out root 2 with 2, and then I have an r squared. And then we have to worry about all this stuff. Cosine theta. The theta is 45 degrees, and so we can simplify that because cosine of 45 degrees is 1 over root 2. Sine of 45 degrees is 1 over root 2. And then we have to add F3. Gm squared over r squared j hat. And now we can combine a bunch of terms. First off, you'll notice that everything has a gm squared over r squared. So let's just pull that out. Gm squared over r squared. And then we're left with a whole bunch of stuff. What do we have? We have 1 I hat. That's this guy right here. For this thing, we've got to move this 2 into there because we have just factored out a gm squared over r squared. So this becomes 1 over 2 root 2 I hat. Take this one right here. And then this guy becomes 1 over 2 root 2 j hat. And then our last one is just right there, 1 j hat. And so finally we can put all these terms together. So what do we get? We get gm squared over r squared. And now we have 1 plus 1 over 2 root 2 I hat. And then we have the exact same thing for j hat. In fact, we can just write it like this. I hat plus j hat. And so let's get it out. We get gm squared over r squared times 1 plus 1 over 2 root 2 I hat plus j hat. That's pretty cool. Why is that cool? Because now it's really easy to calculate the strength of the thing, and it's really easy to calculate the angle. In fact, you already know the angle. The angle has to be at 45 degrees. And if it's I hat plus j hat, it's going up at 45 degrees. But that makes sense. Calculating the magnitude is not too bad. Since now we know the complete angle. Very good. All right. Any questions on that one? Let me know. Good luck. Cheers. Hello class, Professor Anderson here. Let's take a look at an example problem. This is a race car problem. And in this problem it says the following. A race car accelerates around an arc given the following. The initial speed is 0, the final speed is 350 kilometers per hour, and the radius of that arc is 230 meters. Now what they want us to figure out here is what is the tangential acceleration, the radial acceleration, when it's halfway around this arc, and then what coefficient of friction will keep the car on the track. All right, so we got to think about the problem for a second. Let's see if we can draw it out. The very first thing we should always do is just draw it out. So here's our arc. Okay. The semicircle, we know that it is radius L. Now we have a car. And this is a top view of the car, so the car is heading around the track, like so. And it says that when it gets all the way to the end of this arc, it has a speed of vf. It's a little bit outside the frame there, we'll write that here, vf. What we're going to have to figure out is what the tangential acceleration is, what the radial acceleration is, at the halfway point. Okay, so when it's up there, what is it doing? Well, in the problem, they tell us that the tangential acceleration is constant the whole time. So acceleration at the beginning, acceleration there, acceleration at the end, that means the tangential acceleration is going to be the same the whole time. Okay? And to figure that out, let's go back to the kinematic equations. So the kinematic equations say the following. one of those equations is this: VF squared equals VI squared plus 2 times A times how far you've gone. Earlier we said that was delta X, but we can call that delta S in this case, right? How far have you gone? Delta S. All right, that equation looks pretty good. Why does it look good? Because we know this, right? That's our little 350 kilometers per hour. We know this. That is 0. We're looking for A. Delta S, do we have delta S? Sure. We know the radius of this arc. We know that it's going to go from there to there to get to this final speed VF. And so we, in fact, do know delta S because delta S is going to be half of a circle, right? If you go all the way around the circle, it's 2 pi r. Half of a circle is just 5 times r. Since in this equation we're just looking for acceleration, specifically tangential acceleration, and it's the same the whole way, we can pick any beginning point and end point we want. So here's our initial point, here's our final point. And so now we can calculate A sub t rather easily. A sub t, and we just have to solve this equation right here, right? VI, that goes away. This thing is 0. Let's just cross out. Okay. What are we left with? We have a VF squared, and then we have to divide by 2 delta S, but we said delta S was equal to pi r. So we already have all those numbers. Now you have to do one more thing. You have to convert this to SI units, since it's in 350 kilometers per hour. You have to convert that to SI units. So let's do that. I did it earlier. What did I get? I got 97.22 meters per second. I got to check me on that, but I'm pretty sure that's right. And so now if we plug in all those numbers, let's see what we get. So we've got 97.22 quantity squared. We're going to divide by 2, that pi, and then r is 230 meters. Okay. Punch those numbers in your calculator and tell me what you get. Make sure you got what I got, which was, I'm going to put my whiteboard over there, 6.54 meters per second squared. Okay? That was AT. Let's think about how we're going to calculate AR. So as the car goes around, it is not only accelerating because somebody's pushing on the gas pedal, but it is also turning. And anytime you're turning, you are accelerating. This is what we call centripetal acceleration. So centripetal acceleration is given by this A sub r. What is that? It is v squared over r. Okay? That's pretty good, but remember, we're trying to calculate this centripetal acceleration up here at the halfway point. It's obviously going to change as it goes around the track. Right here, it's not moving at all when it first starts. Centripetal acceleration is 0. It's speeding up, we're going to get some value here. It's going even faster there. And so the radial acceleration, the centripetal acceleration will, in fact, change as it goes. All right, so we need to figure out v. How do we calculate this v up here at the halfway point? The way we do that is, again, go back to our kinematic equation. We use this equation as long as we're careful about it. What is v? V